Yes. Yeah. All right. Okay, so it's always good to follow one friend and to be followed up by another friend. So I will talk about the next 20 to 25 minutes about the Indian contribution at Belle+II. And so just to introduce, so this is the sort of the silver jubilee of India's participation with Belle and Belle+II. As you know that Belle officially approved in 1994 and India joined in 1998. So that is the stage we didn't have any opportunity to participate in any detector hardware. And this is the famous CP violation measurement and the subsequent Nobel Prize to Kobayashi and Masukawa. 2010 is when Belle stopped taking data, but then, sort of given the quality and the volume of the data, where there has been still physics result coming out of it. As far as the Belle+II, Belle+II was officially approved in 2010, and India became a member of SPD Layer 4 project. That I will have some slide on that. And SPD has been successfully installed to Belle+II in 2018, and since 2019, we have been taking the data. Okay, so who are we? So this is the sort of the political map, and you can see that the collaboration is spread throughout India, maybe a little bit more concentrated towards the northern part. Probably this is outlier here, and there is on the side, and not to forget on the eastern side. So there are 12 physicists from 10 Indian institutions, and there is one more participant, sort of interest from NIT Jalandhar. The size of India-Belle collaboration is 63, including engineer and technician, and we are the 6th largest collaborating nation. So if you want to miss the next few slides, you can just look at the executive summary. So the key point of the India-Belle collaboration has been the human research development. So we have produced about 27 PhD students, and 21 are working, and 5 of these students and postdoc, they are back in faculty. And in fact, the previous speaker, I mean, he's not one of them, and he was one of the Belle alumni. We have trained a good number of, this undergraduate, master, and project student, and about 10 engineer and technicians that are involved with the detector building. Close to 50 high impact publications with the Indian literature that has come out of this Belle and Belle+II. We have given talk at various high profile conferences. The key hardware contribution, we have involved in the design, prototyping, and construction of so-called the SVD, which is a key component for the science deliverable of Belle+II. We have a modest contribution to the Belle+II computing, and the part, as I said, we are, if you see 63 in a collaboration of 1,000, the leadership position that we have been held in both the collaboration has been significantly larger compared to the size of the collaboration. So here is the canvas of the physics topic. In general, we have been worked on, starting from CK metrology, CP violation, and rare decays. On the charm side, we are also involved in the spectroscopy, rare tau lepton decays, and also the physics performance studies. We hold this so-called annual Belle analysis workshop that has played a key role in sort of germinating and bringing the collaboration together. So here I start with a standard model candle, and in Indian culture, I mean, we always call Ganpati. So this is so-called the angle phi 3 or gamma. It's already shown in the previous yesterday by Diego. So this is theoretically clean. You're talking of a theoretical uncertainty of 10 to the power -7. And the single most precise value comes from our friendly competitor from LSCB. That's the sort of about 4 degree. And here is the result. You can see the combined sort of result coming from the gamma. So 65 plus minus 4. So here we have the first measurement. This is the first measurement, including the Belle data with more improved analysis technique. And the fact is, we have the improved technique available from Belle+II that has been sort of percolated to the analysis. And here we do this so-called model independent Dally-Sprout analysis. I mean, that there is this so-called model dependent Dally-Sprout analysis, but there the problem is you get a sort of irreducible model dependent uncertainty, which you don't, this method is much better on that way. Of course, the statistics is the issue here. So here we take both the B2 d pi and b to dh and d going to k sort hh, both for k pi, k and the pi and more. And here you see the projection of this is on the top on the Belle data using 711 inverse femtobarn, and this is 128 inverse femtobarn. In the projection, this is so-called the energy difference. For the signal, you are expecting to be peak around 0. Since we simultaneously consider both pi and k on, so you see a peak also, I mean 0 for the right mass hypothesis and on the positive side for the wrong mass hypothesis. And the other thing you can see that here, although Belle II has significantly lower data, smaller data compared to Belle, it's very competitive. I mean, if you see the total scale. So we obtain pi 3. I mean, this is a kind of rivalry between, it used to be between Belle and Babbage, like pi 3 or gamma. But anyway, I think both are one and the same. So here the uncertainty is mostly dominated by the statistics 11 degree. And we expect an LSCB like precision with 10 order 1 inverse of data. So we have to wait for a while, but of course the work will continue. What? You're talking of this? Yeah, so this is just to, so you can see if you draw a line here, so this is the Dali's plot projection of the D2 k sort pi pi or k sort kk in this case. If you draw a line over here and you see folding on both sides is symmetric, and this is done what we call the optimal binning. You want to get the best sensitivity to your pi 3, and that's the kind of the bin you get. So 8 bin you have in the D2 k pi pi, and yeah, so this has been done in a very judicious manner. So here you see this, so what we call the Z graph or temperature graph, that essentially says the color code tells you which bin you are talking about. So so you're saying there is a discontinuity across the. Well, it is done in a bin wise. So obviously you have an event either belong to this bin or that bin. So it's not like, I don't know, like what exactly you are trying to say, that continuity and discontinuity. Yeah. Yes, which is this one. Right. So the two.
No, it's treated together. These are bins in which the strong phases have approximately constant values. Yeah. So all the events in the black regions are treated together. All the events in the whatever purple region are treated together, etc., etc. Does this answer the question?
Okay. So now I move on to the second part. This is about the time-dependent CP violation. So here the key parameter to carry out this measurement. So first of all, we are sort of asymmetric collider pretty much at the epsilon 4s, and there is this quantum entanglement. Basically, once you tag the B0 or B0 bar at one point, at that particular point, the other guy has to be the antiparticle of that. And sort of we measure this so-called the delta Z, and once you know the gamma beta, the Lorentz boost factor, from that you can calculate the delta T basically. And the delta Z precision is something like because we have now this slightly reduced boost, so therefore in order to compensate for that, you need a better precision, and thanks to the pixel detector we have, and also 5-layer of strip detector we get. And obviously this new nanobeam scheme that also help. So there is one challenging example in which Indian group is involved. So this is a time-dependent CP study where you are talking of B2K sort pi 0. Now, if you look at this cartoon, so what you have a neutral particle coming in and decaying to 2 neutral particles. This K sort, the other thing is K sort has, it fly certain distance before decaying to charged pion. And this is obviously a neutral pi 0. So, basically from where does this 2 pion coming from? And thanks to the beam spot constraint, we can do a pretty good job. And then you can constrain, you can form a IP tube, sort of technical detail. I don't want to get into that, but it's really challenging measurement. And why it is important, in the standard model, you expect the direct CP asymmetry to be 0, and the so-called the mixing induced CP asymmetry that should be consistent of sin to beta. And Gronau has proposed this so-called isospin sum rule. So you can use this as a litmus test of new physics, that if you look at this particular relation, which is supposed to be 0, in that you measure the different branching fraction and the CP asymmetry of the different B to K pi decay mode. And this particular, all other inputs are very precisely measured. And the one where we are really lacking and need to improve is so-called the direct CP asymmetry for K0 pi 0. Right. So here we have a preliminary result. Sort of first of all, in order to validate this kind of challenging decay channel, we use B0 to Z psi K short, and to mimic your signal, you do not vortex the 2 muon coming from a single point, so that it becomes almost like a Z psi proxy for the pi 0 and then the K short. So that we do to calibrate the signal delta receipt. So since we don't have enough statistics in hand to get a sort of reasonable or sort of a measurement, we fix the SCP to the world average value, and this is the measurement we get right now. Sort of it's not very competitive, but with a small data set of 190 inverse 21, that is the thing, and the work is going on to go for the full what we call the pre-long shutdown data for the publication. Okay, so here is one or a couple of slide I have. This is so-called the famous flavor anomalies. I don't have to really tell this thing that this observable RK or RK star, they are theoretically pristine. One is talking of an accuracy of something like 10 to the power minus 2. And that's the lepton flavor universality. But then you can have lepto quark, or you can have Z prime, and that can affect the observable, this kind of observable. And in these two plots, you see a summary of the measurement from LSCP. Obviously, is the showing the clear evidence of lepton flavor universality violation at the level of 3.1 sigma in the K star. Sorry, RK, I'm sorry. And also here in the RK star. And then we have measurement from Belle, but obviously with a larger error bar, and this was the measurement from Babar. Okay, so so right now we don't have that kind of sort of statistical advantage, competitiveness to, let's say, sort of compete with LSCP. But the point that what Diego mentioned yesterday, that the beauty of Belle+II in this context is that we have got similar sensitivity both for the electron and the muon channel. Just to sort of repeat what he said, you compare the resolution that you achieve. First of all, you look at the x-axis range in both the case, and you see the resolution in both pion and kaon and the background level, and you compare what LSCP has got. But despite the fact that the challenging fact of the electron, getting such a competitive measurement is really, really nice to see. So so where do we stand right now? So we had a preliminary measurement. Well, it's not really measurement in that sense from B to KLL, but that was a tiny set of data. But the work is going on with the full data set. We also had some measurement related to B to K star LL, where we found both the precision for the electron and muon mode are similar. There is slight, electron mode was slightly on the higher side, but that is, we want to see with larger statistics. Excuse me. So what does the future hold in this particular measurement? Here you see with 700 @1 inverse of 0.71 @1 inverse of data, this was the Belle result, whatever has been achieved. And in Belle+II, to get a sort of 10% accuracy, you need 5 @1 inverse of data. And if you look at the luminosity projection, the base or sort of the target things, we're talking of something like 26. But I guess if we are somewhere 25, when you have at least 3 or something like that, we can, although we don't get that kind of precise thing what LSCP has got, but one would like to see which way the things is moving. This is something, a kind of byproduct of the measurement that was done by the IIT Hyderabad group, but it's a very interesting measurement. Here you are assuming, so this is so-called the ratio of F plus minus to F00, which is nothing but the decay ratio of the epsilon 4s going to charged B meson pair or the neutral B meson pair. Assuming isospin symmetry, you can express like that. So this is the signal yield and the epsilon is the efficiency. So in order to measure that, Belle has used its full data statistics and performing this so-called two-dimensional fit. This is so-called the beam energy constant mass, which should pick around the B mass for the signal, and the background is combinatorial. And delta E I have already introduced. For signal, it should pick around 0. And you see very nice signal. And so we determine independently for the muon channel, electron channel, and average of that. So these results are consistent with PDG and the most precise to date. And the other advantage is we have done a pretty good job to take care of the systematics due to the isospin symmetry assumption, based on which you get to this expression. So that's the most dominant systematics. So I think this is an open invitation to our theory colleague to see how best we can work on this. So I move on to the charm decay. So here I start with something which is like, I can say fairly, it will be very difficult. I cannot say impossible, but difficult for LSCB. So this is D0 going to 2 neutral pion. And here we made a measurement of the CP asymmetry, where the flavor of the D0 is determined by the charge of the slow pion that is coming from the D star decay. So here, if you have CP violation, the two height of the two signal modes should be same. Different, and you see they're kind of same, and that is reflected in the measurement we have. So up to precision of 0.6%. This is consistent clearly with no CP violation, but an order of magnitude improvement over the existing result that we had. There is another measurement done by the IIT Bhubaneswar and Aizer Mohali group, looking for CP violation and branching fraction in D0 to K sort. This is again 2 neutral kaon. I mean, this is somewhat bit, I mean, this obviously LSCB can do, but the challenge here, because the K sort flies certain distance before decaying. So here, this used to be the most sensitive measurement of CP asymmetry, and this was, this plot was a old plot, and this was the LSCB RON1 result. But after kind of quite a few trials, they have very recently come up with the result, which has bet the Belle uncertainty, so about 1.2. Our uncertainty was 1.5%. So this is close to the theory limit given here. In terms of the branching fraction, this is the most precise measurement, and there is work is underway from one of the Indian group to look for this D0 to K sort. Okay, so this is very quickly about D0 to gamma. Again, a nice channel to search for BSM physics. And what you see, this is mostly the background. The peak you are seeing, this is obviously not the signal. This is a peak coming from D0 to pi0, and one of the photon either they're not reconstructed or somehow passing through the crack in the detector. So here we put the world's best limit of 8 × 10⁻⁷, and in this plot over here, you see this is the standard model prediction taking the long distance effect into account. So it's 10 to the -8. And there's some incarnation of supersymmetry. MSSM says this was the kind of range. And with the upper limit that we have set, we are kind of sort of restricting that part. So Punjab group is working on for this measurement with the full Belle, with whatever Belle II data we have. And they have already done the identification of the control sample D0 to K sort pi0. Okay, so this one very quickly about this X3872. Some of you would be knowing that this is the most highly, in terms of citation, this is the sort of 2000+ citation, and the highly cited paper from Belle is even more cited than the CP violation observation paper. So here the JPC determination from LSCB clearly says it's 1++, and that says it could be a Charmonium-like particle. But then if it is CI-C1, then the single pionic transition should be suppressed. But base 3 has observed that in this particular case, they see a pretty good, the ratio is 0.88. So this rate is much larger than expected for Charmonium. For example, psi prime, you see the number is 10 to the power minus 3. So motivated by this in Belle, we have searched for this decay. And as you see in this projection here in so-called invariant mass of CI-C1 pi 0, we don't see, sort of no signal. This is where the signal should come. And this is another exotic particle, X3915, where we see about 2 to 2.3 sigma. And so therefore we put upper limit, although our result does not contradict base 3 result. Okay, so just, yes, I have 2 more slides. So this is what I call the provocative statement building the heart of Belle+II. So Indian institutions are involved in the design and prototyping and building of this so-called silicon vortex detector. So there are 4 layer of what I'm saying, layer 3, layer 4, layer 5, yes, 4 layer and 6 layer is what I say, including the pixel. And this is important for the vortexing. Vortexing is crucial for the CP evaluation measurement and charge particle tracking. And we had morning discussion with Tuhin and others that how you can have the SPT only tracking for low momentum. And the other thing that we have shown also that it can also use for identification, the particle identification, especially for low momentum. So this is a kind of a real photograph of a detector, which was built by an Indian team. And just proud to say that this detector is able to measure the charged particle position to an accuracy of 15 to 20 micron. Okay, so since Amol was asking that question, so this is successful R&D with Bharat Electronics Limited, pretty close by here, in developing AC coupled single-sided silicon microscope sensor. This was done keeping in Belle+II upgrade in mind, but as you could imagine, for a low energy experiment such as Belle+II, the material budget is a key criteria, and so therefore single-sided. We have to go to double-sided, and then there are a few other issues. But the fact is we have been successful single-sided. This can be useful for some homegrown experiment, for example, nuclear physics or other experiment, or even some satellite-based experiment where material budget is not such an issue. Okay, so here, this is the penultimate slide, just to show that how the Indian group is also involved with the charge PID identification. So this is a other than the vortexing, this is the second most crucial factor for the success of any flavor experiment. And here our colleague, they have been working on determining the particle identification performance for charged pion and kaon using this particular decay. So this decay is very important and very nice because you don't have to really identify, you use any PID thing just from the charge. As soon as you know the slope pion charge, that tells you the same charge particle that is also a pion and the opposite one has to be kaon. So kinematically you identify the particle and then you can look at the PID information. And this is the kind of state-of-the-art measurement we have based on a likelihood-based hypothesis. People are working on also using the machine learning. So the current result is 87.3% KNID efficiency with a fake rate of about 7.8% pion. That is in data, and this is the number with simulation. And so this is something I thought, since I said SVD can SVD help, and indeed SVD can help for low momentum region less than equal to 1 GeV, and that is clearly shown in the data. And this paper is already, this is part of a SVD paper which has already been accepted in Journal of Instrumentation. Okay, so that brings me to the summary, where I want to say the plans for Belle+II. Basically, the most crucial deliverable from the collaboration is the high quality PhD that we have produced or will continue to produce. The students are really working on the thrust areas of flavor physics. Whatever you name it, we have someone or other working on that. And there are also students are working on the operation and maintenance. Little bit of interest we have. Many of us are overly subscribed on multiple projects and the thing, but on such some small scale, we are involved with some upgrade software side. For the PID particularly, this machine learning technique will help, and work is undergoing on that. Now that SPD is successfully built and delivered, we are working on to take care of this SPD, particularly during the COVID pandemic. Like students took shift operational monitoring shift sitting in India, yeah, I think this is the last thing I don't have to say that. Thank you.
Thank you, Gagan. Floor is open for questions.
I had two questions. One is on the SVD slide. I just wanted to get an idea of the physical size of SVD. There was no human being
Size of the
size.
Okay. Yeah, I should put the protractor. So this is like the layer 3. Jim, sorry, what is the number? 20.
Approximate size. I mean.
I'm just forgetting that. Sorry, I'll give the number. Like I have it, but
no, this much. There's no human being standing next.
Oh
to it.
no, you're talking of this one.
Yeah.
Oh, this one.
This much. The second.
I thought you were saying where they are in the Belle+II. Like what is?
No, I wanted to look at understand the physical scale of this object that you have in the photo.
These are sort of 4-inch. Yeah, so you have 3 modules. So there is 3 sensors. One here, and for this the middle one is where we use so-called the origami concept, and then there is a trapezoidal one. So you can see sort of corner to corner. That's the dia of what we're saying. Okay, there's a little bit of, so yeah, this week.
And the second
I will give you the number, sorry.
That was all I wanted. Yeah. The second was yesterday there was this talk by Sabyasachi, I think. He talked about B going to Ka and axion going to 3 pions.
Yes.
You think something like that is possible to be done at Belle+II?
Yeah, as far as I know, there is some work is going on, but not anyone from Indian side working on that. But yes, it is very interesting. B to Ka, you are saying, right?
And A goes to 3 pions.
Yes. So the advantage will be like as you go to the multi-body decay, so you'll have the low momentum track on an average, and so with the Belle+II detector compared to, let's say, in the Belle data, I mean, we will have a much better competitiveness there. Yeah, so it is possible.
Any more questions to Gagan?
So this is like a question regarding a timeline of the Belle+II program and what lies beyond that. So you had an arrow hitting the 2018 Belle+II, but then what after that?
Which arrow you're talking of? This one?
Towards the beginning of the talk, like you showed the timeline.
Yeah. Right. So right now, as you know that the goal is to accumulate 50 atomic inverse of data, and with the this is a machine where you are looking really. I think the real challenge here, not from the experimental side, the real challenge here from the accelerator side. You are pinching the electron and the positron beam to the level of nanometer. Okay, and at that level, there's lots of challenge our accelerator colleague are finding. So therefore, you see that the way we want to achieve the peak luminosity is not an easy task, So the current projection to get the 50 atomic inverse is you're talking of something like 2032, 33, something of that order. And that's the timeline you are talking of. But even if the Belle+II stop taking data during that, I mean, around the mid 30, let's say, but there will be people are already
Belle+III in the pipeline.
Yeah, so there is, well, there is some talk going on at some level, but there is a connection to whether Japan will host International Linear Collider. I mean, this probably goes to the, I mean, it may be a little bit difficult for Japan to have both ILC and Belle+II, to be fair enough. But if ILC doesn't come in Japan, then I would say, I mean, this is what I'm saying outside. I mean, you can take it a little with pinch of. So the Belle+III definitely is something people are, the Japanese community and the broader community are very much interested, particularly in connection to LSCB. I mean, given the synergy and the complementary environment.
So how about B2 tau tau in your priority list?
Oh yes, that is very much in the priority list, and already we will have one in Belle data itself. We will have we're just going the collaboration wide review is going on, but we will have from both Belle and Belle II. See, I said for the muon and electron, you are talking of 5/1 inverse of data, but K tau tau or K star tau tau, this is something we can do. Obviously, we can improve on the limit and then see. But yeah, this is very much on the priority list.
So even better than LHCb?
Yes, of course. I mean, with the multiple neutrino and the thanks to the you have basically 2B and nothing else. And in LHCb they profit from the high longitudinal boost and the dipole detector. So that's what they do. But in our case, is significantly we should have better sensitivity.
I don't see any more hands raised. So let's thank Gagan.